can. Looking at geometric shapes with three kinds of imaginary directions unlock the secrets of space and time. It sounds wild, doesn't it? Like something conjured purely from abstraction.
Totally science fiction vibe.
Right. But here's the thing. Mathematicians didn't just imagine these structures. They, discovered them through some really rigorous work. And therefore, because these strange, beautiful spaces with their multiple complex dimensions fit so perfectly with the language of fundamental physics, well, they might just be a key to understanding the deepest layers of the universe around us.
That connection is just... it's uncanny, isn't it?
Yeah.
This link between what feels like very abstract geometry and the actual rules governing space-time particles.
Yeah.
That's what makes studying these objects so incredibly compelling.
Yeah.
For mathematicians and physicists.
Absolutely. And today, we are taking a deep dive into your sources about these fascinating mathematical entities. They're called hyperkähler manifolds.
Hyperkähler.
Yeah. And at their heart, they're special types of geometric spaces, smooth manifolds, but with a really rich and specific structure. They have not one, but three distinct complex structures.
Three ways of defining imaginary directions.
Exactly, at every single point. And these three structures, they don't just sit there separately, they interact. They interact in a way that perfectly mirrors the algebra of Hamilton's quaternions. Remember those?
Oh yeah, IJK.
Right, IJK, where I squared equals J squared equals K squared equals IJK equals -1, that whole thing.
That quaternionic structure is definitely one of the defining characteristics. And the other big one is their curvature, right? Their Ricci-flat.
Ricci-flat, yeah. Let's unpack that a little. Ricci curvature is basically a measure of how the volume of tiny little balls on the manifold deviates from flat space.
Like Euclidean space.
Exactly. And Ricci flatness means there's no deviation, zero, which is, as you said, profoundly important in physics.
Especially general relativity.
Yeah.
Vacuum solutions to Einstein's equation spacetime without any matter or energy. Those are precisely Ricci-flat.
So, okay, we've got spaces with this unique quaternion-like structure of complex directions, and they have zero Ricci curvature. Our mission today, in this deep dive, is to unpack the story of these hyperkähler manifolds using your sources.
Trace the history.
Yeah, where did the idea even come from? Why did they go from being like abstract curiosities to these really central objects of study? And how did this field grow into such a vital bridge connecting pure math, differential geometry, algebraic geometry, even number theory with theoretical physics?
String theory, quantum field theory.
Right, all that stuff.
And what's really wild is that this story isn't over. It's not just history.
No, not at all.
I mean, we're starting this journey over 70 years ago with these sort of theoretical possibilities. But the ideas, the structures discovered back then, they are still absolutely crucial today.
Foundational for cutting-edge research, influencing totally new areas.
Yeah.
So we're going to journey through the decades. We'll see how key insights, sometimes from really unexpected corners of math, built on each other.
It's a narrative of, well, slow discovery sometimes. Painstaking work.
Moments of brilliant insight, too, and the power of just connecting different fields.
It leads right up to today's open questions, the stuff people are actively researching now.
Think of it as tracing the lineage, maybe? The family tree of this fundamental geometric concept that seems weirdly woven into the fabric of reality.
It's a story of intellectual pursuit, isn't it? Mathematicians, physicists, sometimes working alone, sometimes collaborating closely, just pushing the boundaries of what we know.
Exactly. So I'm going to try and guide you through this narrative. We'll hit the key breakthroughs, the surprising detours, and some of the fascinating human stories behind these discoveries, too.
And I'll be here, sort of acting as a sounding board, maybe asking some questions you might have too. Try to get at the why, why did this happen then? Why does it matter? Digging into the implications.
Okay, so get ready. It's a journey into some complex ideas, for sure, but hopefully presented in a way that reveals their underlying elegance and, well, their significance. We'll meet some brilliant minds who overcame incredible personal challenges.
Yeah, you mentioned wartime, poverty.
Right. That stuff played a role in shaping this field. We'll see unexpected connections pop up between areas of knowledge that seem totally separate, because ultimately, understanding these complex shapes, these hyperkähler manifolds, it reveals this profound hidden symmetry.
The symmetry in the mathematical world.
Yeah, and it seems to resonate in the physical universe, too. It's a pretty compelling intellectual adventure, I think.
Let's dive in.
Okay, let's unpack this story. So our journey doesn't start with someone saying, hey, let's build a hyperkähler manifold because, well, the concept didn't even exist yet.
Right.
Instead, it begins back in the 1950s with a theoretical possibility, really. A hint of these structures glimpsed within a much bigger, much more ambitious project in differential geometry.
Yeah, the 50s were really about foundational classification in geometry. The big question wasn't how to build these things, but more like, based on fundamental properties like curvature, could spaces like this even theoretically exist? What kinds of geometric symmetries are even possible?
And the key development here, the real seed of the idea, comes from Marcel Berger's classification of holonomy groups. That was 1955.
Holonomy groups. Okay,
Yeah.
maybe we should explain holonomy simply first.
Good idea. Imagine you're on a curved surface, like a sphere.
Okay.
You take a vector, like an arrow pointing straight up maybe, and you move it along a path on the surface, but you always keep it parallel to itself in the local sense. It's called parallel transport.
So you're not twisting it relative to the surface as you move.
Exactly. Now, if you go around a closed loop and come back to your starting point, that vector, it might not be pointing in the exact same direction it started in.
Right, like the classic example.
Yeah.
Start at the North Pole, walk down to the equator,
Mm-hmm.
walk along the equator for a bit, say a quarter of the way around,
Yeah.
and then walk straight back up to the North Pole. The direction you end up facing is rotated 90 degrees from the direction you started walking south.
Precisely. That twisting that happens when you parallel transport vectors around loops. It depends entirely on the curvature of the space inside the loop. And the collection of all the possible transformations, rotations, usually that can happen to a vector after going around all possible loops from a point. That forms a group. That's the holonomy group.
And it captures really fundamental information about the global curvature, the symmetry of the whole manifold, just from looking at this local parallel transport idea.
Exactly. So Berger's work in 1955 was this major theoretical achievement. He systematically classified the possible holonomy groups for certain kinds of Riemannian manifolds, specifically irreducible, simply connected ones that weren't just flat space.
So he figured out the complete list of possible fundamental symmetries these spaces could have in terms of how vectors twist.
Yes. And nestled among the groups he found, and it was a pretty short list actually, it was SPN.
SPNM, the compact symplectic group,
Mm-hmm.
or the quaternionic unitary group.
Right, and that specific group corresponds mathematically to spaces that preserve not just one complex structure, but three distinct complex structures that satisfy those quaternion relations we mentioned.
The IJK structure.
Exactly. So in his big systematic search for all possible geometric symmetries, he algebraically identified the exact group that would correspond to manifolds with this specific kind of three-way complex structure.
Okay, but at that moment, it was purely theoretical, right?
Mm-hmm.
Berger's classification didn't prove that any non-flat manifolds with SPN holonomy actually existed.
No, it didn't, except for NE0, which is just flat space with trivial holonomy.
So he basically just found a potential name for something that might not even exist. Why was that so important? It sounds incredibly abstract.
That's a totally fair point. And it was highly abstract then, but think about it. By identifying SPN as a possible holonomy group for irreducible manifolds, Berger gave mathematicians a precise structure to look for.
Okay, a target.
Exactly. It wasn't just random fumbling in the dark anymore. It was a clear signal that these quaternion-related geometries might exist beyond the familiar stuff. It set a clear goal. Find manifolds whose holonomy is precisely this SPN group.
So it bridged Lie theory, the study of these algebraic groups, with differential geometry.
Yes. It was kind of a quiet revolution hinting at these exotic, highly symmetric geometries that were just waiting to be discovered. It provided the algebraic target.
And this didn't just come out of nowhere, did it? It built on earlier work.
Oh, definitely. It stood on the shoulders of giants like Riemann and Cartan in differential geometry.
And crucially, it also built on the foundational work of Kähler back in the 1930s. His 1933 paper introduced Kähler manifolds.
Right, Kähler manifolds. Those are the ones with three compatible structures. A Riemannian metric for distance, a complex structure for complex coordinates, and a symplectic form, which is related to area or phase space in physics.
And hyperkähler manifolds are a very special, much more structured subtype of Kähler manifolds.
And Erich Kähler himself, his story adds a real human dimension here, doesn't it?
It really does. He was this brilliant German mathematician. His work on Kähler manifolds was absolutely fundamental, linking complex, symplectic, and Riemannian geometry. But his life was deeply impacted by World War II.
He served in the German military, and then after the war ended, he was held in POW camps in France for a couple of years, right? Until 47.
Yes, imagine that. imprisoned after the war. But even in that situation, his mathematical reputation was such that other prominent mathematicians like Élie Cartan in France actually made efforts to get him mass books and papers while he was in the camps.
That's incredible. Finding solace, continuing his thinking, even in confinement, it really speaks to the power of mathematics, doesn't it? To provide structure and meaning even amidst total chaos.
Absolutely. So, wrapping up the 50s, we have Berger, building on Kähler and others, identifying this SPN group as the algebraic target for a potential exotic holonomy. The possibility is there, the structure is defined, but nobody has actually proven that a non-flat manifold with this structure exists or found an example yet.
Okay, so Berger sets the algebraic target, SPNN, in the 50s. The 1960s then shifted focus, right? Moving from just abstract possibility to figuring out, okay, what concrete geometric properties would a manifold with this holonomy have to have?
Exactly, and maybe starting to identify existing types of manifolds that might fit the bill.
Yeah, researchers started digging into the geometric implications. If these things did exist, what specific verifiable characteristics would they possess?
And a key breakthrough came almost simultaneously, independently, from two mathematicians, Edmond Bonin in France and David Kranz in the U.S., both in 1966.
1966. Okay, what did they find?
Working separately, they both proved that any Riemannian manifold with SPN holonomy must have something called a parallel four-form.
Yeah.
And crucially, they showed its manifolds must be Ricci-flat.
Okay, break those down. Parallel four-form. What's a four-form and what does parallel mean here?
So a differential form is basically something you can integrate over surfaces or volumes of a certain dimension on your manifold. A four-form deals with four-dimensional volumes. Parallel here means the same thing as with vectors. If you parallel transport this four-form around any loop, its value doesn't change, it stays constant.
So it's like this intrinsic geometric signature that exists everywhere on the manifold and remains constant, reflecting some deep symmetry.
Precisely. Having a parallel, non-degenerate four-form is a very strong constraint. It's a distinct hallmark of this specific geometry, capturing how the metric works with those three complex structures.
Got it. And the other property, Ricci-flatness, we mentioned the zero Ricci curvature, and its importance in physics, vacuum solutions, and GR.
Yes. Ricci-flat means locally. Volumes behave just like in flat Euclidean space. No average curvature, making small balls shrink or swell compared to flat space. And like we said, in physics, vacuum solutions to Einstein's equations are Ricci-flat. So Bonin and Crane's result immediately flagged these potential SPN holonomy manifolds as highly relevant to theoretical physics.
Potential models for gravity and empty space.
Exactly.
So this was a huge step. We had Berger's algebraic target. Now we knew that if these manifolds existed, they must have these very specific geometrically and physically significant properties. A parallel four-form and Ricci flatness.
It seriously constrained the search, and it highlighted their potential relevance right away. It also showed how powerful tools like differential forms could be for probing geometry.
And the fact that Bonin and Cranes found this independently in the same year.
Classic simultaneous discovery. It's just the ideas were sort of in the air, right? Two sharp minds tackling the problem, maybe from slightly different angles, but arriving at the same fundamental geometric consequences of Bonin holonomy.
Yeah, that's always striking. I gather Cranes' work, maybe cited a bit less often sometimes, was just as critical in establishing these properties.
Absolutely. Both were crucial. Their results really solidified what these potential manifolds would look like geometrically, if they existed.
But they still hadn't actually found one, right? A concrete, non-flat, compact example confirmed to have SPN holonomy and thus these properties. They knew what it should look like, but hadn't identified one yet.
That's where the work of Kunihiko Kodaira comes in, even though he wasn't directly looking for SPN holonomy at the time.
Kodaira, what did he do?
Between roughly 1964 and 1968, Kodaira undertook this massive project, classifying compact, complex surfaces. These are complex manifolds of dimension 2.
So four-dimensional real manifolds with a complex structure.
Right. Kodaira was a brilliant Japanese mathematician, a Fields medalist known for mixing algebraic and analytic techniques. He systematically classified these surfaces based on their fundamental properties. And in his classification, he identified a very special class he named K3 surfaces.
K3 surfaces, what makes them special?
Algebraically, they have what's called a trivial canonical bundle and zero irregularity. These are technical properties related to their complex structure and cohomology.
And it turned out, looking back later, that these K3 surfaces are exactly the simplest compact examples of what we now call hyperkähler manifolds.
Exactly. Kodaira's classification provided this tangible class of known objects. Suddenly, mathematicians had something concrete to study to see if it actually possessed the CPN holonomy properties identified by Berger, Bonin, and Cranes.
So K3 surfaces became the poster child example.
Pretty much. It gave the abstract theory a home in a specific, well-understood class of spaces. And the name K3 is a nice nod to history, right? Referencing Kummer, Kähler, and Kodaira himself.
That ties the lineage together nicely.
Yeah. Kodaira's work was really pioneering blending techniques and helping solidify Japan's growing prominence in algebraic geometry. He didn't call them hyperkähler, that name came later, but his work provided the crucial candidates.
Okay, so by the end of the 60s, we have the abstract target, SPN holonomy. We know the required properties, Ricci-flat parallel four-form, and we've identified a class of existing objects, K3 surfaces, that are the prime suspects.
The stage was perfectly set for the 1970s, where the crucial proofs and constructions would finally tie it all together.
The 1970s. Okay, this feels like the decade where the pieces really clicked into place. The concept finally gets a name, some major conjectures get proven, and the first explicit examples are actually constructed.
Yeah, this is where hyperkähler geometry as a defined field is truly born. The links were made definitive. It showed that those K3 surfaces Kodaira found do have the geometric properties Bonin and Cranes predicted, and therefore the holonomy group Berger identified.
Let's start with Beauville, Shapiro, and Shafarevich. Their work on the Torelli theorem for algebraic K3 surfaces in 1971.
Right. The Torelli theorem is a fundamental result in algebraic geometry. For K3 surfaces, it basically says that the surface is determined, up to geometric equivalence, isomorphism, by its Hodge structure.
Hodge structure. Remind us briefly. It's about how the cohomology of the manifold, which tells you about its overall shape, its holes, decomposes into pieces based on the complex structure. It's a richer invariant than just the topology.
So, Beauville, Shapiro, and Shafarevich showed that for K3s, if two have the same algebraic fingerprint in their Hodge structure, they must be the same geometric shape.
Essentially, yes. It translates the geometric classification problem into an algebraic one, connecting it to things like lattice theory, a really powerful tool for telling K3 surfaces apart. And these guys, Beauville, Shapiro, and Shafarevich, were major figures in the Soviet mathematics school during that incredibly active period.
Okay, so that gave an algebraic way to classify the candidates, but the big question remained. Do K3 surfaces actually have that crucial Ricci-flat metric with SPN holonomy that Bonin and Cranes said was necessary?
And this is where one of the absolute monuments of 20th century geometry comes in, Shing-Tung Yau's proof of the Calabi Conjecture. This was between 1976 and 1978.
Ah, the legendary Calabi Conjecture, proposed by Eugenio Calabi way back in 1954.
Exactly. Calabi conjecture that on any compact Kähler manifold whose first Chern class vanishes, which K3 surfaces do, there exists a unique Ricci-flat Kähler metric in each Kähler class. It linked this algebraic property, vanishing first Chern class, to the existence of this very special metric.
And Yau proved it.
He did, using incredibly sophisticated techniques in partial differential equations, specifically the complex Monge-Ampere equation.
And why was this so earth-shattering for hyperkähler geometry?
Because for K3 surfaces, Yau's proof definitively answered the question.
Yes.
A Ricci-flat metric does exist on them. Now remember, K3s are complex dimension 2. There's a fundamental result linking holonomy and curvature, which says a Ricci-flat Kähler manifold of complex dimension 2 must have holonomy SU2.
And SU2 is actually the same group as SP1.
Bingo. So Yau's proof confirmed it. K3 surfaces, the ones Kodaira classified, do have SP1 holonomy, the N-of-1 case of Berger's target, and they do have the Ricci-flatness Bonin and Cranes predicted.
Wow. So that was the existence proof for compact, non-flat examples of these things.
Exactly. It was monumental. It bridged algebraic geometry, the vanishing Chern class, with differential geometry, proving the metric exists via hard PDE analysis. It was a real tour de force, requiring Yau to develop entirely new techniques.
And Yau's personal story behind this achievement is just incredible.
It truly is. Born in China, family fled to Hong Kong, grew up in extreme poverty.
Father was a philosophy professor.
Yeah, who died when Yau was young, making things even harder. Yau even admitted to falling in with a street gang for a while.
No way!
Yeah. But his intellectual curiosity, especially for geometry, which he said helped him understand his father's philosophy, that became his driving force. He studied math, got his PhD under the great S.S. Chern at Berkeley, and then proved the Calabi conjecture when he was only 28.
28, and that led to the Fields Medal.
Yep, Fields Medal at 33. An amazing story of resilience and the power of mathematical passion.
Incredible. So Yau proved compact K3s exist with the right metric. What about the name hyperkähler and constructing other examples?
That brings us back to Eugenio Calabi himself, the one who made the conjecture Yau proved. In 1979, Calabi published a paper where he did two key things. First, he constructed explicit examples of Ricci-flat kähler metrics with SPN holonomy, but on non-compact spaces.
Like the cotangent bundles of complex projective spaces, TCPN.
Exactly those. And second, in that same paper, he formally introduced and used the term hyperkähler to describe manifolds with SPN holonomy.
So Yau proved they exist for compact K3s. Calabi showed how to build some non-compact ones and gave the field its name.
Precisely. Calabi's constructions were vital because they gave people concrete formulas to work with, explicit metrics to study, and coining the name hyperkähler formalized the field, gave it a clear identity. His construction method also introduced a technique that became really important later, the hyperkähler quotient.
And the name itself, hyperkähler, just means more Kähler.
In a sense, yeah. A standard Kähler manifold has one complex structure compatible with the metric and symplectic form. A hyperkähler manifold has three I, J, K, satisfying the quaternion rules. So hyper refers to this extra triplet structure, this richer symmetry.
Makes sense.
So Calabi's ingenuity in construction, combined with Yau's groundbreaking existence proof, the 1970s really were the birth decade for hyperkähler geometry as we know it.
Okay, so by the end of the 70s, we have the name. Existence is proven for K3s. Some non-compact examples are built. The 1980s must have been when things really took off in terms of finding more examples.
Exactly. The 80s saw an explosion of activity. The focus shifted really intensely towards finding new examples, especially compact ones in higher dimensions, and developing systematic ways to construct them.
Moving beyond the four-dimensional K3 surfaces.
Right, showing that this hyperkähler phenomenon exists in higher dimensions, two dimensions that are multiples of four, actually.
And a huge step in constructing these higher dimensional compact examples came from Arnaud Beauville in 1983.
Yes, Beauville, a leading French algebraic geometer. He introduced the concept of irreducible symplectic manifolds. These are essentially the higher dimensional analogs of K3 surfaces in the hyperkähler world.
How are they defined?
They're simply connected compact Kähler manifolds with a unique, non-degenerate holomorphic 2 form, a symplectic form compatible with the complex structure. For compact manifolds, these properties turn out to be equivalent to being hyperkähler with SPN holonomy for N1.
And crucially, he actually built compact examples of these.
That was the massive breakthrough. Beauville constructed the first known compact hyperkähler manifolds in dimension greater than 4. He found two infinite series of them.
Infinite series? How did you build them?
One method used Hilbert schemes of points on K3 surfaces. The other used generalized Kummer varieties.
Hilbert schemes. So you take a K3 surface, our known 4D example, and you look at the space that parameterizes like all possible sets of endpoints on that K3 surface.
That's the idea of the Hilbert scheme.
Yeah.
Of it next. And Beauville proved that this space itself is a compact hyperkähler manifold of dimension 4n.
Wow. So you generate dimension 8, 12, 16 hyperkähler manifolds just by looking at configurations of points on a K3.
Exactly. It was this incredibly powerful construction method using moduli spaces, spaces that parameterize geometric objects. It showed you could generate infinite families. His work also revealed a lot about their structure, like introducing the now central Beauville-Bogomolov quadratic form on their cohomology.
Building higher dimensions from points on lower ones. Cool. And related to these moduli space ideas, Shigeru Mukai found something similar in '84.
Yeah, Mukai, another prominent Japanese mathematician, showed that other kinds of moduli spaces related to K3 surfaces are also hyperkähler, specifically spaces that parameterize stable sheaves or vector bundles on K3 surfaces.
So the space of certain types of bundles living on a K3 surface is itself hyperkähler.
Precisely. These moduli spaces are often deformation equivalent to Beauville's examples, meaning they're in the same family. But this directly connected moduli theory, the study of spaces classifying geometric objects right into hyperkähler geometry.
Another huge source of examples.
Yep, and it revealed deep connections between the geometry of the base K3 and the geometry of the space of objects living on it. Mukai's work was super innovative.
Okay, so we have constructions from points on K3s, constructions from bundles on K3s. Was there a more general systematic method developed?
That brings us to Nigel Hitchin and his development of the hyperkähler quotient in 1987.
This sounds like it might be related to Calabi's earlier quotient idea.
It is, but much more general and systematic.
Yeah.
Hitchin developed this powerful tool for constructing new hyperkähler manifolds. You start with a known, often simpler hyperkähler space, and you take a quotient by the action of a group, but in a very specific way that preserves the hyperkähler structure.
Using something called a moment map.
Exactly. It's analogous to the symplectic quotient in symplectic geometry, but adapted for the three complex structures of hyperkähler geometry. You essentially divide the space by the group action while keeping the hyperkähler property intact.
So it's a machine for generating new examples from old ones.
Pretty much. And it's incredibly versatile. It yields many important examples and provides a natural framework for understanding metrics like the Eguchi-Hanson metric, which was found earlier but fully understood through these quotient methods.
And Hitchin himself, he's a major figure, right? Working across geometry, topology, physics.
Absolutely legendary. And a fascinating background, working-class roots. Parents encouraged him. Then this appendix operation during his crucial exams forced him to just lie in bed and focus intensely on math and physics. Kind of set his path.
Wow. And his collaborations, like the ADHM construction.
That's another amazing story of parallel discovery. The ADHM construction, describing instantons in physics, was found independently around the same time by Hitchin and Atiyah in Oxford, and by Drenfeld and Menin in Moscow.
Right across the Cold War divide.
Exactly. Atiyah famously told the story of their excitement only to get a letter from the Soviets with the same results. Shows how math ideas converge globally.
Incredible. Okay, so the 80s. A real explosion. Finding ways to build new hyperkähler manifolds by taking points on K3s, looking at spaces of bundles, using Hitchin's quotient machine. Is there a pattern here?
Yeah, it seems many of the successful construction methods rely on building up from simpler known examples like flat space or K3s, or by leveraging these related algebraic structures like moduli spaces or structure-preserving group actions. It was a decade of ingenuity in building powerful systematic tools.
Okay, after that 80s explosion of examples and construction tools, the 1990s feel like maybe a time for consolidation, organizing all this new knowledge.
That's a good way to put it. The 90s were really crucial for solidifying the theoretical understanding of compact hyperkähler manifolds, proving big classification theorems, developing more systematic framework, like building the definitive library for all the discoveries so far.
And a cornerstone of that effort was Misha Verbitsky's global Torelli theorem in 1996.
Yes. This was a huge generalization of the Torelli theorem for K3 surfaces that Piatetsky, Shapiro, and Shafarevich proved back in the 70s. Verbitsky's theorem applies to higher dimensional compact irreducible hyperkähler manifolds.
And what does it say, basically?
It says that these manifolds are determined not quite up to exact geometric equivalence, but up to birational equivalence by their period points.
Okay, unpack birational and period points.
Birational equivalence is a bit weaker than isomorphism. Two algebraic varieties are birationally equivalent if they're basically the same, except possibly on some lower dimensional pieces. Think of it like they could be transformed into each other by algebraic surgeries, blowing up or blowing down parts.
So, fundamentally related, but maybe differing in some small areas.
Kind of. And the period point captures information about the manifold's complex structure encoded in its Hodge structure, how its cohomology decomposes. The period map sends the manifold to a point in this big complex space called the period domain.
So Verbitsky showed the period point determines the manifold, up to this birational equivalence, and maybe some group action.
Exactly, modulo the action of the monodromy group, which accounts for how the period point can shift as you deform the complex structure. This is a massive classification result. It connects the deep geometry to algebraic and topological data, a powerful tool. Verbitsky, a prominent Russian mathematician part of that post-Soviet diaspora, was also known for using preprints early on, speeding up how results got shared.
And speaking of that monodromy group, A.O. Markman studied its actions specifically for those moduli spaces on K3 surfaces, also in '96.
Yes. While Verbitsky's theorem was very general, Markman focused on the concrete examples, the Hilbert schemes and moduli spaces of sheaves on K3s built by Beauville and Mukai. He studied how the monodromy group actually behaves for those specific spaces.
Why is understanding that monodromy, how things change as you move around, important?
It tells you about the global structure of the space of all possible complex structures on that type of manifold, the Teichmuller space. Markman showed how the monodromy group acts via reflections related to the geometry of divisors on the manifold. His work provided concrete details that complemented Verbitsky's more abstract theorem. Markman's an expert at linking geometry, cohomology, in these moduli spaces.
Okay, classification via period points, understanding the monodromy. What else was key in the 90s consolidation?
Daniel Huybrechts played a really important role in synthesizing the knowledge base. In 1999, he published a paper that was basically a comprehensive summary of the fundamental properties of compact hyperkähler manifolds known at that time.
Like the essential guidebook.
Pretty much. He covered their cohomology rings, the structure of the Kähler cone, which describes possible metrics, the period map, the Beauville-Bogomolov form, all the key structural elements.
So if you were new to the field then, that was the paper to read.
Absolutely. Huybrechts unified results from the 80s and 90s into a coherent framework. He's known for really clear explanations, which is invaluable in such a technical field. His synthesis made things more accessible and provided a standard foundation.
So the 90s were about tidying up, proving big classification theorems, writing down the fundamentals.
You could say tidying up, but tidying up in advanced math often means proving incredibly deep and difficult theorems like Verbitsky's global Torelli. These aren't just summaries. They're proofs that establish the bedrock structure, the foundation needed for the next stage of discovery. It was a vital phase.
Right. So moving into the 2000s, with those foundations solidified, did things continue along those lines, or did new directions open up?
The 2000s definitely pushed in new directions.
Yeah.
People kept trying to find genuinely new examples beyond the known families, and there was also this major shift towards using powerful abstract tools, especially from category theory.
Still searching for new shapes, then?
Oh yeah, and it paid off. Kieran O'Grady made a major discovery in 2003. He constructed a new type of compact, irreducible hyperkähler manifold.
A new type. Didn't Beauville find infinite families?
He did, using Hilbert schemes and Kummer varieties. But all the manifolds within those families are deformation equivalent. You can continuously morph one into another within the space of hyperkähler manifolds. O'Grady's example was huge because it was one of the very, very few known examples that did not belong to Beauville's families. It represented a fundamentally new deformation type.
Like finding a completely different species after mapping out the main families.
Exactly. It showed the classification wasn't complete with Beauville's work. There were these unexpected, maybe sporadic examples out there.
Yeah.
As construction was really intricate, often involving resolving singularities of certain moduli spaces again. Moduli spaces proving fruitful. O'Grady's work really highlighted that finding truly new compact examples is still a major challenge.
Okay, so a rare new shape was found. But you also mentioned this turn towards abstract tools, categories. What on earth does category theory have to do with geometry?
That brings us to the really influential work of Tom Bridgeland, especially his introduction of stability conditions on derived categories of K3 surfaces around 2002.
Stability conditions, derived categories, sounds intimidatingly abstract.
They are pretty abstract. Category theory gives you this very general language for talking about mathematical objects and the relationships between them. A derived category is this sophisticated algebraic construction built from things like vector bundles or sheaves on a manifold, but it captures more complex relationships and hidden symmetries.
Okay, so different mathematical language to describe geometric stuff. And stability conditions.
Stability conditions, in this context, are a way to sort of organize or filter the objects within that derived category. They give a notion of stability, similar to how stability is used classically to construct moduli spaces, but now in this abstract categorical setting. Bridgeland showed the space of all possible stability conditions on a K3 surface is itself a complex manifold with interesting geometry.
And how does this connect back to hyperkähler geometry?
It brought these powerful categorical methods right into the heart of the field. It gave researchers completely new tools for studying moduli spaces of sheaves on K3s, which we know are often hyperkähler, for understanding how these spaces change as you vary parameters, something called wall crossing, and for revealing deeper symmetries that you just don't see by looking at the manifold itself. Wow! This framework became absolutely central for understanding things like mirror symmetry in a mathematically rigorous way. Bridgeland's work, done quite early in his career, had a massive impact, won him major prizes.
So, the 2000s. A rare new geometric example surfaces, and this whole new abstract categorical language gets introduced to study them. Feels like the field is simultaneously finding specific objects and creating entirely new ways to talk about them.
Exactly. The toolkit was expanding dramatically. And to help digest all these sophisticated new ideas, especially around moduli spaces, Daniel Huybrechts teamed up with Manfred Lehn to write a comprehensive textbook, The Geometry of Moduli Spaces of Sheaves, published in 2006.
So after his 1999 synthesis paper, Huybrechts co-authors the standard grad textbook on the topic, pulling all this new stuff together.
Precisely. It became the reference, consolidating work by Mukai, Beauville, Bridgeland, O'Grady, and many others. It covered constructions, stability conditions, geometric properties, made these advanced topics accessible for a new generation. Len's collaboration with Hybrex really shaped the modern understanding and teaching of this area.
Okay, so the 2000s, new examples, radical new abstract tools, and foundational textbooks. Sounds like a period of both discovery and real maturation for the field.
It definitely was. And that trend of finding deeper connections continued strongly into the 2010s, linking hyperkähler geometry to even more surprising areas like number theory and dynamical systems. It just shows how deeply embedded these special shapes are in the bigger mathematical picture.
The 2010s. Okay, after the new examples and the categorical tools, what were the big themes? Exploring even deeper, maybe unexpected connections.
That's a great way to put it. The field kept building on geometry, algebra, categories, but the 2010s saw really striking results connecting hyperkähler geometry to arithmetic geometry and the study of dynamical systems.
Let's start with Francois Charles's result in 2013. That sounded important.
Very significant. Charles is an expert in arithmetic geometry, and he proved the Tate conjecture for K3 surfaces defined over finite fields, an odd characteristic.
The Tate conjecture definitely sounds like number theory.
It is. It's a major conjecture in arithmetic geometry. It tries to relate algebraic cycles, basically, geometric shapes defined by equations inside your variety, to Galois representations, which are deep objects from number theory encoding symmetries related to field extensions.
So Charles connected hyperkähler geometry via its fundamental K3 example directly to a major question in number theory.
Exactly. His proof showed that these specific geometric objects, K3 surfaces, have precisely the kind of arithmetic properties predicted by this major number theory conjecture. It provided crucial evidence for the conjecture and built this amazing bridge between geometry and number theory.
Geometry talking to numbers. Wild. What about the categorical ideas from the 2000s? Did that continue?
Absolutely. Nicholas Addington in 2016 explored new derived symmetries of hyperkähler varieties.
More symmetries, not just geometric ones like rotations.
Right. He looked at the autoequivalences of their derived categories, those abstract algebraic structures encoding info about sheaves. Addington found surprising symmetries within these categories that do not correspond to any simple geometric transformation of the manifold itself.
So the algebraic language of the derived category has its own hidden symmetries that the shape itself doesn't obviously show.
That's the idea. It revealed even deeper, more abstract layers of structure residing purely in the categorical realm. It showed the derived category is richer than just being a mirror of the smooth geometry. Addington's work beautifully links abstract categories to concrete geometry, and it's relevant for physics, too, like understanding D-brane categories in string theory.
Okay, connections to number theory, uncovering deeper abstract symmetries. What about Misha Verbitsky again, building on his classification work?
Verbitsky stayed very active. In 2013, he studied the action of the mapping class group on the cohomology of hyperkähler manifolds.
Mapping class group, what's that?
It's the group of topological self-transformations of a manifold ways you can twist and stretch it and bring it back onto itself, up to continuous deformation. Verbitsky proved this remarkable result. The mapping class group acts ergodically on the Teichmüller space of hyperkähler manifolds.
Ergodically. That sounds like it relates to randomness or dynamics.
It does. It means that under these topological twists and stretches, the orbit of almost any complex structure eventually gets arbitrarily close to every other possible complex structure for that deformation type. It sort of mixes everything up thoroughly.
Wow. So it brings this dynamic, almost chaotic perspective to classification.
Exactly. It built on his earlier global Torelli theorem, but used methods from dynamical systems and ergodic theory. It really shows the field becoming more interdisciplinary, drawing powerful techniques from different areas to tackle geometric questions.
So the 2010s, connecting shapes to number theory, abstract symmetries, even dynamics and randomness. How does all this cross-pollination help?
These deep connections are crucial. They show hyperkähler manifolds aren't just isolated curiosities. They're part of this huge interconnected mathematical tapestry. Understanding their arithmetic, their categorical structure, their dynamics, it reveals insights and opens paths for proof that you just wouldn't find by looking only at their smooth geometry. It's about seeing the same object from many different angles, and each view enriches the whole picture.
Okay, so we've traced this incredible journey. 50s glimpse, 60s properties and candidates, 70s birth and proofs, 80s construction explosion, 90s classification, 2000s new examples and tools, 2010s deep connections. Where does this leave the field today? What are people working on right now?
It's still an incredibly active and central area in both math and theoretical physics. Building on everything we've discussed, researchers are pushing forward on several key fronts.
What are some of the main directions?
Well, that challenge of constructing genuinely new, compact, irreducible hyperkähler manifolds, beyond Beauville's families and O'Grady's example, that's still a major open problem. People are exploring new techniques, maybe using generalized geometry, new takes on twistor theory, trying to find these elusive shapes.
So finding new examples is still a big driver.
Absolutely. Alongside that, there's intense research into their birational geometry, especially in higher dimensions, using tools like Bridgeland's stability conditions, ideas from the minimal model program, trying to understand how different hyperkähler manifolds relate through these birational transformations.
And the categorical side, derived categories.
Still huge. Building on Bridgeland and Addington, mathematicians like Aaron Bayer, Emmanuel Macri, Laura Pertusi, they've made fundamental contributions to stability conditions and using them to probe the geometry and birational geometry of these manifolds and their moduli spaces. The derived category is seen as encoding incredibly deep information.
What about the arithmetic connections from the 2010s?
That's also growing. Beyond the take conjecture for K3s, people are studying hyperkähler varieties over different kinds of fields, like Padic fields from number theory, further strengthening those links.
Any totally new areas popping up? Machine learning, maybe?
There's some early exploration into using computational methods, like machine learning, maybe to help classify or study metrics, but it's very experimental still. And there's ongoing interest in potential quantum information theory connections, given the links to gauge theory and string theory.
Speaking of physics, how vital are these manifolds in current theoretical physics?
Absolutely foundational. In string theory, compact hyperkähler manifolds, as special Calabi manifolds, are key target spaces. Moduli spaces of instantons in gauge theory are often hyperkähler. Their role in mirror symmetry is fundamental. Physics often provides motivation and intuition that leads to math breakthroughs and vice versa.
Still very much thriving at that intersection.
More than ever, progress often happens when ideas cross over. It's truly interdisciplinary. Differential geometry, algebraic geometry, arithmetic, representation theory, category theory, physics, all talking to each other.
So what are the biggest open questions driving researchers today?
Well, like we said, the complete classification of compact, irreducible hyperkähler manifolds is still wide open. Are Beauville's families and O'Grady's example all there is, or are there more? Understanding the detailed geometry of the known higher dimensional examples is also tough. They're way more complex than K3s. And just exploring the full implications of all the categorical and arithmetic connections is a huge ongoing project.
It feels like we've come such a long way, from just an abstract possibility of SPN holonomy to building and classifying examples, finding links to physics and number theory, but there's still this vast unknown frontier.
Exactly. It's been an incredible narrative, hasn't it? Berger's hint, Bonian and Crane's finding properties, Kodera classifying K3s, Yau's epic proof, Calabi naming the field and building examples. Then Beauville, Mukai, Hitchin creating this explosion of examples and tools. The 90s classifying with Verbitsky, Markman, Huybrecht synthesizing. The 2000s with O'Grady's new type, Bridgeland's categories, the Huybrecht's lane book, and the 2010s connecting to arithmetic via Charles and dynamics via Addington and Verbitsky.
It's a story of brilliant minds, building piece by piece, overcoming obstacles, driven by sheer curiosity about mathematical structure.
And those human stories, Kähler and the POW camp, Yau's journey, Hitchin surgery, the parallel discoveries, they're all part of this grand scientific narrative.
So let's bring this back around for you, our listener. We've taken this deep dive into your sources about hyperkähler manifolds.
These incredibly special geometric structures, right, defined by those three quaternion-like complex directions and being Ricci-flat, living right at that fascinating border between pure math and physical reality.
And we've seen how they weren't just discovered fully formed, but slowly uncovered, piece by piece, named, built, classified over decades, driven by brilliant people, unexpected connections, and this constant back and forth with physics.
And diving into this, guided by the sources you shared, hopefully gives you a unique window into how fundamental math discoveries actually happen. There's often not a single aha moment, but this long, winding, collaborative process, building on what came before, taking surprising turns, revealing deeper and deeper patterns.
Like uncovering this hidden, intricate symphony written in geometry and algebra.
And what's just fascinating, given all this progress, all this deep understanding we've gained, we found these shapes that perfectly embody quaternion algebra are crucial for physics. But we still don't even know all the shapes of this type that exist.
That's genuinely mind-bending after tracing the whole history.
It is. It just leaves you wondering what other incredible geometric structures, maybe other hyperkähler forms or entirely new kinds of spaces, are still out there waiting. What deeper truths about reality might they reveal? Truths we can't even properly ask the questions for yet. That's the thrill, the unknown, that keeps mathematicians and physicists digging into this amazing corner of the universe.